It begins in silence. Imagine standing outside on a clear, moonless night. The air is still, perhaps carrying a slight chill that makes the barrier between you and the sky feel thin. Above you the world ends and the universe begins. The sky is not just black, it is a deep, endless velvet so dark that the stars seem not to hang in it, but to have been punched through it. Thousands of pinpricks of light glitter, some steady, some twinkling, all impossibly far away. You see clusters of them like spilled sugar in the faint milky brushstroke of our own galaxy. In this moment you feel two things at once. You feel small, standing on the surface of a tiny spinning ball of rock. But you also feel grounded. Your feet are planted firmly on the earth. You feel solid present. You look up at those distant fires in the sky, and a question perhaps unspoken surfaces. What holds them up? What keeps those clusters together? And what keeps you right here from simply floating away into that vast, cold emptiness? We are taught that the space between us and the stars is a vacuum and emptiness. But the silence of the cosmos is deceptive. It is not empty, it is governed. There is a presence in that void that connects you at this very moment to the farthest star you can see. It is an invisible force, a fundamental rule of the universe working tirelessly, silently, and everywhere at once. It is the sculptor of worlds, the choreographer of the cosmic dance. It is the universe's silent architect. This architect has a name, one we all know, gravity. But to name it is not to understand it. We will not speak of it in the language of mathematics, of complex equations or numbers with many decimal places. To understand this architect, we must first understand its nature, its intention. Gravity is not a force in the way we think of a push or a pull like a rope. It is something deeper. It is a property of existence itself. It is the universe's fundamental longing. Think of it as the cosmic glue. In a universe that began with an explosion, an event that sent everything flying apart, gravity is the counterforce. It is the whisper that says, "Come together." It is the force of connection. It pulls matter toward matter, not out of aggression, but out of a fundamental need for proximity. It is also the universe's great embrace. It is a gentle, persistent hold. It is the embrace that keeps the Earth's atmosphere wrapped around us like a thin blue blanket, protecting us from the harshness of space. It is the embrace that holds the water in our oceans, stopping it from spinning off into the void. On a grander scale, it is the embrace that holds the moon in a perfect looping dance around the Earth and holds the Earth in turn in its steady orbit around the Sun. It is the embrace that gathers billions of stars like our Sun and holds them together to form the massive spinning island of light we call the Milky Way. This architect is everywhere. It is the anchor that gives you weight, that holds your home to the ground, that pulls the rain from the clouds. And it is the grand designer that arranges galaxies into magnificent spiral arms and glittering clusters. Our first introduction to this architect is often simple and profoundly familiar. It is the dropped glass that shatters on the floor. It is the heavy feeling in our legs as we climb a steep hill. It is the slow, graceful descent of a falling leaf. The most famous story, of course, is that of an apple falling from a tree. The legend of Isaac Newton and the apple endures not because it was the first time anyone had seen something fall. It endures because it marks a moment of profound connection. The genius was not in seeing the apple fall to the ground. The genius was in asking if the very same force that pulled the apple from the branch also reached higher. Did it reach the top of the mountains? Did it perhaps reach all the way to the moon? He realized that the force pulling the apple and the force holding the moon in orbit were one and the same. This was the moment we understood. The architect that governs our small everyday lives, the simple act of falling, is the exact same architect that builds and governs the heavens. Its signature is written on the smallest and largest of scales. To truly appreciate the work of this architect, we must for a moment imagine its absence. What if gravity simply stopped? The thought is more terrifying than a simple feeling of weightlessness. If the architect's embrace were to suddenly vanish, you would no longer be held to the earth. You, your chair, your home. The trees and the oceans would instantly be flung off the surface by the planet's own rapid rotation. The Earth itself, no longer held together by its own immense gravity, would crumble and break apart, its compressed core exploding outward. The air in our atmosphere, no longer glued to the planet, would immediately expand and vanish into the cold of space and the sun. Our star is a magnificent balancing act. It is a massive ball of gas trying to explode outward with the heat of its nuclear furnace while its own gravity desperately tries to crush it inward. Without that inward pull that embraced the sun would detonate in a single catastrophic explosion ending our solar system. Across the cosmos, the stars would all do the same. The galaxies no longer held together would fly apart. The universe would not be a beautiful collection of structures. It would be a cold, thin, disorganized soup of particles. It would be a formless mist, a chaotic, lonely and homogeneous fog with no structure, no planets, no such stars, and no life. The universe we see is not that mist precisely because the architect was there from the beginning. Its job is not just to maintain order, but to create it. Long before there were planets or people or even stars, the universe was just that, a vast, dark and almost uniform cloud of hydrogen and helium gas. It was a blank canvas. It was the raw material. How do you build a home from a formless mist? How do you create light in an endless darkness? You use gravity. You instruct the silent architect to begin its work. This architect's first, greatest and most important masterpiece was the star. The creation of that first point of light in the dark was the architect's first great project. It was the moment gravity took the chaos and began to build. This is where the story of all cosmic structure begins. Let us now explore how this silent architect took that first chaotic dust, that cold and formless mist, and began its first great work forging the stars. Across the vast, silent stretches of the universe, space seems to be an endless empty black. But this void is deceptive. It is not truly empty. Floating in the darkness between the stars are the largest structures in our galaxy, immense ghostly clouds of gas and dust. We call these majestic clouds nebulae. They are the birthplaces of stars, the cosmic nurseries where light itself is born. These clouds are staggeringly huge, spanning many light years across. A single light year, the distance light travels in 1 year, is already trillions of kilometers. These nebulae dwarf our own solar system to an almost unimaginable degree, and they are incredibly cold, hovering just a few degrees above absolute zero, the coldest temperature possible. They are made almost entirely of the simplest element in the universe, hydrogen. For every million atoms of hydrogen, there might be a few 100,000 atoms of helium, and perhaps only a few tiny frozen particles of dust, microscopic grains of carbon and silicon, like cosmic smoke. For eons, these clouds just drift. They are dark, quiet, and seemingly permanent, holding all the raw material needed for creation, waiting for a trigger. In this cold, dark expanse, a silent, patient force is always at work. It is the most fundamental force in the cosmos, gravity. Gravity is weak. The gravitational pull between two single atoms of hydrogen is almost zero. But in a cloud that contains the mass of thousands or even millions of suns, this tiny pull adds up. Gravity is also relentless. It never sleeps, it never stops pulling. Over millions and millions of years, this persistent tug begins to draw the scattered particles of gas and dust closer together. Imagine an enormous invisible net slowly tightening. The cloud, which was once spread out and thin, begins to fragment. It breaks into smaller, denser clumps. This process is incredibly slow. From the outside, nothing appears to be happening. But inside, gravity is patiently sculpting. Sometimes this slow collapse is triggered or hurried along by a shockwave from a distant exploding star, a supernova, or the gravitational disturbance from a passing galaxy. This external push gives gravity the advantage it needs, helping to compress regions of the cloud and start the process of star formation. Bit by bit, particle by particle, gravity pulls the raw materials of the universe into concentrated pockets. The cold, empty void begins to focus. As gravity pulls the gas and dust inward, the particles are forced into a smaller and smaller space. This is compression. Anyone who has pumped air into a bicycle tire knows what compression does. It creates heat. As the particles of gas and dust are crushed together, they collide with each other more and more often. These collisions generate friction, and that friction generates heat. The cloud clump, which was once just a few degrees above absolute zero, starts to warm up. At this very center of this collapsing clump, the pressure is the greatest. This center becomes the core. As more and more material falls inward, adding to the weight, this core gets denser and hotter. This baby star is now known as a protostar. It is not a true star yet, but it is a glowing ball of gas heated entirely by the crushing force of its own gravity. It glows a dull red, buried deep within the dusty cloud it was born from. This stage can last for hundreds of thousands of years. The protostar continues to feed, pulling in more and more gas and dust from its surrounding cocoon, growing heavier, denser and hotter by the moment. It is like a cosmic pressure cooker building up an incredible temperature and pressure in its heart. The core of the protostar continues to shrink and heat up. The temperature climbs from thousands to hundreds of thousands and then to millions of degrees. Finally, it reaches a magic number about 10 million degrees Celsius or 15 million Kelvin. At this unbelievable temperature and under this immense crushing pressure, the very nature of matter changes. The hydrogen atoms in the core, which are really just single protons, are moving at an incredible speed. They are packed so tightly that the normal force that keeps them apart is overwhelmed. The protons slam into each other with such violence that they fuse together. This is the moment of ignition. This is nuclear fusion. In this process, 4 hydrogen protons are forced together to become one new heavier particle, a helium atom. But if you were to weigh the new helium atom, you would find it is slightly lighter than the 4 original hydrogen atoms combined. A tiny fraction of the mass has disappeared. It hasn't vanished. It has been converted into a colossal amount of pure energy. This is the power that Albert Einstein described with his famous equation energy equals mass times the speed of light squared. The lost mass is transformed into a flash of gamma rays, a burst of pure, powerful light and heat. This is the divine moment. The protostar ignites. It switches on its nuclear engine. It stops being a hot, dark ball of gas heated by gravity and becomes a true self-sustaining brilliant star. A new light shines in the universe. Gravity was the midwife of this birth. It did all the hard work of squeezing and compressing the material until the conditions were perfect. But the life of the star comes from this new nuclear fire burning deep within its core. This single event is the most important act of creation in the cosmos. Every speck of natural light you have ever seen from our sun, or the distant stars, comes from this very process. Now that the star is born, a new question arises. If gravity is still pulling inward, why doesn't the star keep collapsing until it crushes itself into a tiny point? And if the nuclear fusion is pushing outward, why doesn't the star just explode like a giant bomb? The answer is that the star immediately finds a perfect, beautiful balance. The entire life of a stable star like our sun is a cosmic tug of war between 2 mighty forces. On one side, you have the relentless inward pull of gravity. Gravity is constantly trying to pull all the star's gas toward the center to make the star smaller and denser. On the other side, you have the new immense outward push from the nuclear fusion in the core. This is called radiation pressure. It is the force of all the light photons and heat generated by fusion pushing their way out from the center, trying to blow the star apart. For billions of years, these two forces fight each other to a perfect standstill. The inward crush of gravity is exactly matched by the outward blast of nuclear energy. This stable balanced state is known as hydrostatic equilibrium. Hydro means fluid. The star is a fluid of hot gas, and static means still or unchanging. The star finds a perfect size and temperature where these two forces are equal. This balance is the single most important reason that life is possible on Earth. Because our sun is in hydrostatic equilibrium, it is stable. It doesn't suddenly get twice as hot or shrink to half its size. It shines with a steady, reliable output of light and heat day after day, million after million of years. This stability provides the long-term consistent energy that planets need to develop complex chemistry and eventually life. The star born from gravity's patient squeeze now uses its own internal fire to fight that same gravity, creating a stable home for the planetary systems that form around it. The new star, our sun, was now blazing in the center of its new domain. But the process of birth is a messy one. The great collapse that formed the sun did not use up all the material from the giant molecular cloud. A vast amount of gas dust and ice, the leftovers from the sun's formation, was still swirling around the newborn star. This material didn't just float aimlessly. Because the original cloud was slowly spinning as it collapsed, it had to spin faster and faster. Think of an ice skater pulling in their arms to spin more quickly. This spinning motion saved the leftover material from falling into the sun. Instead, gravity and motion worked together to flatten this spinning cloud into a massive spinning disk. This structure is called a protoplanetary disk. It was enormous, stretching out for billions of kilometers, far beyond where the most distant planets orbit today. This disk was the nursery for our solar system. It was not a peaceful place. It was a rotating cosmic construction site, thick with the raw ingredients for worlds. Gravity was the project manager. Its work had only just begun. This disk was not uniform. Close to the fiery new sun, it was incredibly hot. Any ice like water ice or frozen methane instantly boiled away into gas. Only materials with very high melting points like metals, iron, nickel and rock silicates could survive in solid form. Farther out beyond a point we now call the frost line, the universe was cold. Here the sun's heat was weak. In this frigid zone, water, ammonia and methane could freeze into tiny solid ice crystals. This difference was the single most important factor in deciding what kind of solar system we would get. Now gravity's second act began accretion. This is a simple-sounding word for a process that is both patient and incredibly violent. It is the process of building big things by sticking smaller things together. It started at the microscopic level. In the swirling disk, tiny dust grains, smaller than particles of smoke, began to collide. At first, they were probably held together by simple static electricity like a sock clinging to a sweater in a dryer. They formed fluffy dust bunnies floating in space. As these clumps grew bigger from dust bunnies to pebbles, gravity began to take notice. A pebble-sized object doesn't have much gravity, but it has some. When two pebbles drifted near each other, their tiny gravitational pull was just enough to draw them together. They stuck. Now the object was a rock. This rock-sized object had slightly more gravity, making it easier to attract other pebbles. This is the rich get richer rule of the cosmos. The objects that by pure chance got a head start and grew a little bigger had a gravitational advantage. They began to pull in more and more material from the disk around them. The process snowballed. Pebbles became boulders. Boulders collided and stuck together, forming objects the size of mountains. These objects, now kilometers across, are called planetesimals, which means tiny planets. These were the true seeds of the planets. Now the game changed. Planetesimals had serious gravity. They were no longer just gently bumping into each other. They were actively pulling each other in. The solar system became a chaotic construction zone filled with millions of these mountain-sized and larger bodies all orbiting the sun, all interacting. Collisions were happening constantly. Some were gentle mergers. Many were catastrophic high-speed impacts that shattered the planetesimals, sending them back to square one. But gravity is patient. Over millions of years, the pieces would regroup and try again. The biggest planetesimals became gravitational bullies. They swept through their orbital paths, pulling in everything they encountered. They grew from mountain-sized to moon-sized. We call these objects protoplanets or planet embryos. And here the frost line made its crucial difference. In the inner solar system close to the sun, the only building materials were rock and metal. Because these materials were rare in the original cloud, there just wasn't much to build with. The protoplanets that formed here, the embryos of Mercury, Venus, Earth, and Mars, grew by colliding with other rocky bodies, but they stayed relatively small. They could not grow large enough to have gravity strong enough to hold on to the light gases like hydrogen and helium that were still floating around. The powerful solar wind from the young sun blew those light gases away from this inner region. But in the outer solar system, beyond the frost line, the story was completely different. The building blocks were not just rock and metal, but also ice, and there was vastly more ice than rock, perhaps 10 times more. The planetesimals here grew incredibly fast, feasting on this abundant icy material. The embryos that would become Jupiter and Saturn quickly became massive, easily 10 times the mass of the entire Earth. Once they reached this critical size, their gravity became so powerful that they could do something the inner planets could not. They began to pull in and capture the lightest and most abundant gases in the entire disk, hydrogen and helium. They entered a phase of runaway growth. Like giant vacuum cleaners, they sucked in gas from the surrounding nebula, swelling to become the gas giants we see today. Jupiter, the first and largest, became so massive that its gravity began to stir the entire solar system. The planets further out, Uranus and Neptune, also grew large from the icy materials, but they formed later or in a less dense part of the disk, so they captured less gas, becoming ice giants. After about 100 million years, the disk was mostly used up. A few larger winners, the planets had emerged. Each one was a survivor built from the wreckage of countless failed planetesimals, its victory secured by gravity. Gravity didn't just build the planets, it gave them their marching orders. It organized the chaos into a stable, predictable system. This is the dance of the solar system. Think of trying to swing a ball on a string around your head. Your hand is the sun providing the central gravitational pull. The ball is a planet. The string is the force of gravity. The ball is moving fast sideways. Its own momentum wants it to fly away in a straight line, but the string gravity constantly pulls it inward. When these two forces, the go-straight momentum and the pull-in gravity, are perfectly balanced, the ball settles into a stable repeating path. This path is an orbit. Each planet in our solar system is in this exact same state of perfect balance. It is constantly falling toward the sun, but it is also moving so fast sideways that it constantly misses. This falling and missing is what creates its orbit a stable path it can follow for billions of years. This order wasn't established immediately. The early solar system was a violent, unstable place. The orbits of the giant planets, especially Jupiter and Saturn, probably moved. Many theories suggest Jupiter may have first drifted inward toward the Sun, scattering rocky material before being pulled back out by Saturn's gravity. This grand migration would have wrecked any early planets in its path, but may have been responsible for delivering water-rich asteroids to the inner solar system, the very water in our oceans. This early dance was a violent brawl. Planets were thrown into new orbits. Some protoplanets may have been thrown out of the solar system, entirely banished to wander interstellar space as rogue planets. What we see today is the stable arrangement after all that chaos. Gravity sculpted the final system. It carved out the gaps between the planets. A planet is defined not just by being round, but by having cleared its neighbourhood. This means its own gravity has become the dominant force in its orbit, either by vacuuming up all the nearby debris or by using its gravity to slingshot that debris away. This is why the path of Earth's orbit is relatively empty, while the asteroid belt is a region full of planetesimals that were never allowed to form a planet, thanks to Jupiter's massive gravity constantly stirring them up. The final arrangement is a masterpiece of gravitational balance. The Sun holds the planets hold their moons. Even the planets pull gently on each other, subtly adjusting their orbits in a complex multi-billion-year rhythm. This is the dance of gravity, a dance of stability won from chaos. And why does this stability matter? Because it is the most crucial ingredient for life. Life as we know it is a delicate and very slow process. It took hundreds of millions of years for the first simple single-celled organisms to appear on Earth. It took billions of years for those simple cells to evolve into the complex plants and animals we see today. This slow, patient miracle of evolution could only happen on a stage that was stable and reliable. Gravity provided that stage. By locking Earth into a stable, nearly circular orbit, gravity ensured our planet received a steady, reliable supply of energy from the Sun. We are kept in the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist on our surface. Imagine if our orbit was unstable. Imagine if every few million years a gravitational nudge from Jupiter sent Earth spiraling closer to the Sun, boiling its oceans, or drifting farther out, flash, freezing the entire globe. Life would never have had a chance. It would be reset to zero again and again. Gravity also gave us bodyguards. The enormous gravity of Jupiter, our big brother, patrols the outer solar system. It acts as a giant cosmic shield, using its gravity to eject many comets and asteroids that might otherwise head for the inner solar system and strike Earth. While impacts still happen, they are far less frequent than they would be without Jupiter. Even our planet's stable tilt, the one that gives us predictable seasons, is held in place by the stabilising gravitational pull of our own moon. Without the moon, Earth's axis would wobble chaotically, leading to extreme and unpredictable changes in climate. The stability created by gravity is not just a feature of our solar system. It is the precondition for our existence. It is the silent, patient force that built our home and then protected it for the 4.5 billion years necessary for us to evolve and one day look up and wonder about it. You do not have to look billions of kilometers into space to feel this force. Gravity's dance is happening right here, right now, in a way you can see and measure every single day. Go to any beach on Earth and watch the ocean. You will see the tides. The water level slowly rises, covering the shore, and then hours later, it slowly falls back, revealing the sand. This rhythmic breathing of the ocean is a direct visible connection between Earth and the Moon, driven entirely by gravity. Here is how it works. The Moon's gravity is pulling on the entire Earth, but it doesn't pull on every part of the Earth equally. It pulls strongest on the part of Earth closest to it, and weakest on the part of Earth farthest from it. The solid rock of the Earth moves as one piece, but the oceans are liquid and they are free to move. The ocean water on the side of the Earth facing the Moon is pulled the strongest, creating a bulge of water that we see as a high tide. But what about the other side? The solid Earth itself is being pulled away from the water on the far side. This leaves that water behind, creating a second bulge and a second high tide on the opposite side of the planet. As the Earth spins on its axis, your spot on the coast is carried through both of these bulges, giving you 2 high tides and 2 low tides approximately every 24 hours. The Sun also has a gravitational pull that creates tides, but because it is so much farther away, its effect is weaker than the Moon's. When the Sun, Earth, and the Moon are all in a straight line during a new moon or a full moon, their gravity adds together to create extra high swing tides. When they form a right angle, their forces partially cancel, creating weaker neap tides. Every time you see the tide come in, you are witnessing a direct gravitational link between our world and our lunar companion. It is the same force that flattened the protoplanetary disk, the same force that built the Earth from dust, and the same force that holds our planet in its life-giving orbit. The tide is a humble daily reminder that we are not isolated. We are bound to the cosmos by an invisible, powerful, and life-giving force. For a long time we have been looking at the small details, the planets, moons, and the single star, our sun, that holds our local family together. We have explored the rocky inner worlds and the giant gassy outer worlds. But this neighbourhood, our solar system, is just one single tiny house on an impossible browser, non-streaming, no tool call in previous turnably vast street. Now we must pull the camera back further and further until our entire solar system, with its giant planet Jupiter and its long-tailed comets, shrinks to a single invisible speck of dust. What we find when we zoom out this far is staggering. Our sun is not alone. It is just one star, one point of light in a colossal collection of other stars. It's not one of 1,000 or even one of 1,000,000. Our sun is one of hundreds of billions of stars, all bound together by their shared gravity. This enormous collection is our home. We call it the Milky Way galaxy. These are the islands of light in the great dark ocean of the cosmos. Each galaxy is an island universe separated from its neighbours by millions of light years of cold, near-perfect vacuum. The scale is difficult to hold in the human mind. If our sun were the size of a single red blood cell, the Milky Way galaxy would be as large as the entire United States. It is a spinning city of light so vast that a beam of light, the fastest thing in the universe, takes 100,000 years to travel from one side to the other. For centuries we looked up and saw this milky band of light across the sky, not realising we were looking into the disk of our own island, seeing the combined light of billions of distant neighbours. And when we built powerful telescopes, we discovered that the fuzzy little smudges of light beyond our galaxy were not just clouds. They were other galaxies, other islands, each with its own billions of stars, planets, and possibilities. But these beautiful swirling islands of light presented astronomers with a terrible fundamental problem, a mystery that threatened to break our entire understanding of physics. It all started when we tried to measure how they spin. We can use an analogy. Think about our solar system. It is held together by the gravity of the sun, which contains over 99% of all the mass. The planets orbit the sun, but they do not all orbit at the same speed. Mercury, the closest planet, must travel incredibly fast at nearly 50 kilometers per second to avoid falling into the sun. Neptune, the farthest planet, plods along at a very slow 5 kilometers per second. This makes perfect sense. The rope of gravity is strongest near the center of the sun and gets much, much weaker the farther out you go. Therefore, objects on the edge must move slowly, or the weak gravitational rope will snap and they will fly off into space. Astronomers assume galaxies work the same way. When we look at a typical spiral galaxy, we see a bright, dense center called the bulge, where billions of stars are packed tightly together. This bulge, just like our sun, clearly contains most of the visible mass. Therefore, we expected stars far out on the edge of the galaxy's disk to be moving very slowly, just like Neptune. When astronomers like Vera Rubin first managed to measure these speeds in the 1970s, they found something shocking, something that could not be true. The stars on the outer edge of the galaxy were not moving slowly. They were moving incredibly fast often, just as fast as the stars much closer to the center. This was a crisis. Imagine a child's merry-go-round spinning at high speed. The horses on the inside are fine, but a horse placed on the absolute outer rim would be flung off instantly. The galaxy was spinning so fast that according to our laws of gravity it should be flying apart. The rope of gravity from all the visible stars, gas and dust we could see was not nearly strong enough to hold on to those fast-moving outer stars. The visible galaxy, the beautiful spiral of light we see in pictures, was behaving as if it were just the tip of the iceberg. The math was undeniable. The galaxies were spinning so fast they should have disintegrated billions of years ago. Yet here they are. They are stable. This means one of two things. Either our understanding of gravity, the laws laid down by Newton and Einstein, is completely wrong, or there is more stuff out there. A lot more stuff we cannot see. This leads us to one of the most profound and humbling discoveries in all of science. The problem was solved by introducing a new mysterious ingredient to the universe. We call it dark matter. Dark does not mean it is black or shadowy. It means it is utterly, completely invisible. It does not glow, it does not reflect light, it does not block light, it does not interact with atoms or light or energy in any way we can currently measure. It is not dust or dead stars or black holes. Scientists looked for all those things, they simply do not add up to the mass required. Dark matter is something else entirely, a new kind of substance that is not part of the normal matter that makes up you, me, and the planet Earth. But it has one single critical property: it has mass. And because it has mass, it has gravity. This is the solution to the Great Spinning Mystery. The visible galaxy of stars is just the decoration. It is sitting inside a much larger invisible halo of this dark matter. Think of it like a scaffolding, the invisible steel framework of a skyscraper. When you look at the building at night, all you see are the lights in the windows. But what holds the building up, what gives it structure and strength, is the massive unseen steel skeleton inside. Dark matter is the skeleton of the galaxy. The fast-moving stars on the outer edge aren't being held in place just by the gravity of the stars they can see. They are being held in place by the immense gravity of this giant invisible sphere of dark matter that surrounds the entire galaxy. This unseen scaffolding provides the extra gravitational rope needed to keep the galaxy from tearing itself apart. How much of this stuff is there? The answer is the most shocking part. When scientists did the math, they found that all the matter we know, the atoms, the elements, the stars, the planets, the gas, makes up only about 15% of the total matter in the universe. The other 85% is this invisible dark matter. We are in effect living on the foam of a vast invisible ocean. Our islands of light are just the visible glowing parts of a much larger, darker structure, this dark matter. This invisible scaffold is not just a minor addition. It is the main ingredient of all cosmic structures. It is what dictates where galaxies form and how they are held together. This invisible scaffolding and the violent history of the universe is what gives the islands of light their beautiful and varied shapes. Galaxies are not all identical. Like trees in a forest, they have different forms based on their age, their environment, and their life history. The most famous and beautiful are the spiral galaxies. Our own Milky Way is a spiral, as is our nearest large neighbour Andromeda. These are defined by a bright central bulge of older stars surrounded by a thin, flat, rotating disk. This disk is where we find the stunning spiral arms. These arms are not solid structures, they are density waves, like a slow-moving traffic jam in the disk. As gas and dust clouds move through this jam, they get compressed, which triggers a massive wave of new star formation. This is why the arms are so bright and often bluish, that they are filled with giant hot young blue stars that burn brightly and die young. Spirals are active star-making cities. Then there are the elliptical galaxies. These are entirely different. They are not flat disks, but rather giant three-dimensional ovals like a fuzzy football, or a stretched-out sphere. They range in size from small dwarfs to the largest and most massive galaxies in the universe. Unlike spirals, they have very little gas or dust. Because they lack the fuel gas to make new stars, they are filled almost exclusively with very old red dim stars. They are often called red and dead galaxies, like giant cosmic retirement homes. So why the difference? How do these two main types form? The answer in large part is collisions. Galaxies, each wrapped in its giant invisible halo of dark matter, are constantly moving through space-time. Sometimes their paths cross. Over millions of years, they pull on each other with gravity, and sometimes they merge in a slow-motion catastrophic collision. When two spiral galaxies collide, the stars themselves almost never hit each other, as space is mostly empty. But their powerful gravity tears both galaxies apart. The delicate spiral arms are ripped to shreds, and the 6 stars are flung about into new randomized orbits. Even more importantly, the vast clouds of gas and dust from both galaxies do slam into each other, triggering a starburst, a single enormous event that uses up all the available gas in a massive bonfire of star creation. After the chaos of the merger settles down, what is left? The 2 spirals have combined into one new giant galaxy. It has no more gas left to make new stars. Its stars are no longer in a neat flat disk, but are now buzzing around in all directions, forming a giant 3-dimensional elliptical shape. This is how many of the giant elliptical galaxies are born. They are cannibals that grew large by eating their neighbours. Sometimes we catch this process in the act. When we see a galaxy that is a chaotic, misshapen mess with no clear structure at all, we call it an irregular galaxy. These are often small galaxies, or they are the snapshot of 2 larger galaxies in the middle of a violent gravitational tug-of-war. From a single solar system, we have zoomed out to see the truth. We live inside a vast island of 100 billion stars. This island is just one of trillions in the observable universe. And these beautiful islands of light are only the visible part of the story, like foam on the waves. The real structure, the invisible scaffolding that holds them together and dictates their shape, is the vast unseen mystery of dark matter. the true architect of the cosmos. As we pull our viewpoint back, way back, individual galaxies like our own, Milky Way, begin to shrink. First they look like bright pinwheels, then bright smudges, and finally just tiny points of light, like single grains of sand on an infinite beach. We are now looking at the universe on its largest and most majestic scale. What we discover is that these points of light are not scattered randomly like salt tossed on a dark table. Instead, they are organized. The universe has a structure, a grand architecture, and the architect is the one force we have known all along: gravity. Even at this immense distance, gravity is relentless. It never sleeps and its reach is infinite. Just as it pulls a moon around a planet and a planet around a star, it pulls galaxies toward each other. When we look at any one galaxy, we almost always find neighbours. Our Milky Way is part of a small collection of about 50 galaxies called the Local Group. This includes the large Andromeda Galaxy, which is currently moving toward us, destined for a cosmic collision billions of years from now. This Local Group is like a small quiet neighbourhood, but the universe has bustling cities. These cities are called galaxy clusters. A cluster is a massive gathering, a dense collection of hundreds or even thousands of galaxies, all trapped together by their mutual gravity. Imagine a space hundreds of times larger than our local group, but crammed with galaxies. They orbit a common centre of gravity, but their orbits are chaotic like a swarm of bees. The space between them isn't empty either. It's filled with a superheated invisible gas so hot that it glows in X-ray light, which our regular eyes cannot see. What holds these enormous cities together? When astronomers measured the speed of the galaxies swirling inside these clusters, they found a huge problem. The galaxies were moving so fast that the gravity from all the stars and gas we could see should not be enough to hold them. The clusters should have flown apart long ago. This was one of the first and most powerful pieces of evidence for dark matter. We realized that the glowing galaxies are just the sprinkles on top of a much larger, heavier, and completely invisible cake. This dark matter provides the extra gravity, the invisible scaffolding that holds the entire cluster together. So a galaxy cluster is mostly a giant spherical cloud of dark matter with thousands of galaxies trapped inside it. Gravity doesn't stop there. Just as it groups galaxies into clusters, it groups the clusters themselves into even bigger structures. These are called superclusters. A supercluster is not as tightly bound as a cluster. It's more like a collection of cities and towns, clusters and groups that are all located in the same general state or country. They are all being gently pulled toward a common centre, but they are so far apart that many may never actually merge. We live in one. Our local group, along with our nearest large city, the Virgo cluster, which contains about 2,000 galaxies, and many other groups and clusters, are all part of a single gigantic structure. We call this the Virgo supercluster. It is a sprawling collection of perhaps 100,000 galaxies stretching over 100 million light-years across. For a long time, we thought this was one of the biggest things in the universe. But in 2014, astronomers realized that even the Virgo supercluster is just one part of an even larger structure. They mapped the motions of all the galaxies around us, tracing the rivers of gravity that they were following. They discovered that our Virgo supercluster is just one suburb of a monumental supercluster they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is our true home supercluster. It contains the equivalent of 100,000 million suns and stretches for over 500 million light-years. Every galaxy in this region, including our own, is flowing toward a single massive point within it, a place astronomers call the Great Attractor. Now we zoom out one last time. We see Laniakea and we see other similar superclusters. What does the map of all of them look like? This is where the true picture, the grandest design of all, is revealed. This is the cosmic web. Imagine a three-dimensional spider's web filling all of space. This web is made of long, delicate threads that stretch for hundreds of millions of light-years. These threads are called filaments. Along these filaments, like beads on a string, are the galaxies and galaxy groups. The filaments twist and turn through space, and where they meet, they form dense, bright knots. These knots are the superclusters of the big cities like Laniakea. This is where most of the matter is concentrated. The vast, massive galaxy clusters are found at the very centre of these intersections where gravity is strongest. But the web is only half the picture. What about the spaces between the threads? These are called the cosmic voids. These are not small gaps. They are mind-bogglingly enormous regions of empty space. They are vast, dark bubbles that can be hundreds of millions of light-years across. They are not perfectly empty. A few lonely galaxies might drift through them, but they are mostly just silent dark emptiness. The universe, it turns out, is mostly made of these voids. The filaments and superclusters where all the life and light exist make up only a small fraction of the total volume. The structure of our universe is like a sponge with small, dense regions of sponge, the filaments and huge holes, the voids. This entire breathtaking structure, this cosmic web of filaments, knots and voids, is the masterpiece of gravity. It is the result of a slow, patient sculpting process that has taken the entire age of the universe to complete 13.8 billion years. It all started at the Big Bang. The newborn universe was almost perfectly smooth, filled with an almost uniform soup of matter and energy. But almost is the most important word. There were tiny microscopic differences in density. Some spots were just a fraction of a percent denser than others. For 13.8 billion years, gravity has been working on those tiny differences. Where there was slightly more matter, gravity was slightly stronger. This stronger gravity pulled in more matter from its surroundings. This made that spot even denser, giving it even more gravity. It's a rich get richer process. The invisible dark matter formed this web first, creating a giant invisible scaffolding. The regular matter, we can see the gas and dust, then fell into this scaffolding, lit up by stars, and became the galaxies we see. At the same time, the spots that started with slightly less matter had weaker gravity. They couldn't compete. Their neighbours stole their matter, and these regions were hollowed out, becoming the great cosmic voids. So the cosmic web is a direct, large-scale photograph of those tiny quantum seeds of imperfection that existed in the first second of time, amplified by gravity over billions of years. It is a spectacular and beautiful network, and it is the largest thing we know. When a star is born, it begins a lifelong battle, a perfect balance between two colossal forces. Gravity, the relentless force that pulls everything together, constantly tries to crush the star into the smallest possible space. But at the star's core, the intense pressure and heat created by gravity ignite a powerful engine, nuclear fusion. This engine fuses atoms together, releasing a tremendous outward blast of energy and light. This outward pressure, the push of fusion, perfectly balances gravity's pull. Our sun is in this stable, balanced phase right now, but this balance cannot last forever. The nuclear furnace at the star's core is not an infinite resource. It has a limited supply of fuel, first hydrogen, then helium, and in larger stars, even heavier elements. A star's entire life is a story of burning through this fuel while gravity waits patiently. What happens when the fuel finally runs out? When the last of the fusible elements is used up, the furnace goes cold, the outward pressure stops. Suddenly there is nothing to fight gravity. The battle is over and gravity wins. The star collapses under its own immense weight. This final catastrophic collapse is what we call the death of a star. The story of this death and what kind of corpse the star leaves behind is determined by a single factor: its mass. The more massive the star, the more dramatic its end. The queered end. White dwarfs. Let's first consider stars that are all like our own sun, or anything up to about 8 times its mass. When these stars exhaust their hydrogen fuel, they don't die instantly. They first puff up into an enormous red giant, expanding so much they might even swallow their inner planets. During this phase, they fuse helium in their core, but eventually the star just isn't massive enough to create the pressure needed to fuse heavier elements like carbon. The fusion engine sputters and dies for good. The star's outer layers, which are only loosely held, drift away into space. They are gently puffed off, creating a beautiful, colourful and ghostly cloud of gas, known as a planetary nebula. What is left behind is the star's core. Gravity crushes this core, but the collapse is stopped by a new strange kind of pressure. It's a quantum mechanical force called electron degeneracy pressure. You can think of it like this. The electrons in the atoms are being squeezed together, but electrons hate being in the same place with the same NRO, or they push back. This electron push is incredibly strong. It's strong enough to stop gravity, but only after the core has been compressed to an unbelievable density. The result is a white dwarf. This stellar corpse contains about the mass of our sun, but it's crammed into a sphere only the size of the Earth. A single teaspoon of white dwarf material would weigh as much as an elephant, perhaps 15 tons. This white dwarf is no longer a star. It makes no new heat. It is just a glowing hot ember, shining with its leftover thermal energy. Over trillions of years, far longer than the current age of the universe, it will slowly cool down, fading into a cold, dark, black dwarf. This is the likely quiet fate of our own sun. The violent end. Supernovae and neutron stars. But what if the star is much bigger? Let's say between 8 and 25 times the mass of our Sun. These stars live very different lives. Because they are so massive, their gravity is much stronger, which means their core furnaces burn much, much hotter. They live fast and die young. While our Sun will live for 10 billion years, a massive star might live for only 10 million years. These giant stars have enough pressure in their cores to fuse elements all the way up the periodic table. They fuse hydrogen to helium to carbon to neon oxygen, silicon, and finally all the way to iron. Iron is the ultimate ash. Fusing iron into a heavier element doesn't release energy, it consumes energy. When the star's core becomes a solid ball of iron, the furnace doesn't just go cold, it's like it hits a brick wall. In less than a second, the outward pressure vanishes. Gravity wins instantly and catastrophically. The iron core, which is already the size of the Earth, collapses. In a fraction of a second, it shrinks to a ball perhaps only 20 kilometers, about 12 miles across. The collapse is so violent that it smashes the atoms themselves. Electrons are forced into the protons, a process that creates a new particle, a neutron. The entire core becomes a giant single atomic nucleus made almost entirely of neutrons. This collapse is stopped by a new forced neutron degeneracy pressure. The same rule as before, but now for neutrons. Meanwhile, the star's outer layers, which were also falling inward at a fraction of the speed of light, come crashing down. They hit this newly formed and unthinkably hard neutron core and bounce. This rebound, combined with a massive shockwave of energy and particles from the core, triggers the most powerful explosion in the universe, a supernova. The star tears itself apart. The blast is so bright that for a few weeks it can outshine its entire home galaxy. This explosion is one of the most important events in the cosmos. It is in these few violent moments that all the heavy elements, the oxygen we breathe, the calcium in our bones, the gold in our jewelry are forged and scattered across the galaxy, seeding the next generation of stars and planets. We are all literally made from the ashes of supernovae. After the smoke clears, what's left behind? If the remnant core is not too massive, it will be that ball of neutrons we described, a neutron star. It has more mass than our Sun, yet it is the size of a city. It is the second densest object in the universe. A single teaspoon of neutron star material would weigh over 4 billion tons. The ultimate end. Black holes. We have one more path. What if the star was truly a giant more than 25 or 30 times the mass of our Sun? The same process begins. The star runs out of fuel. It builds an iron core. The core collapses. But this time the star has so much mass that gravity is completely overwhelming. The collapse begins and nothing can stop it. Not electron degeneracy pressure, that is overpowered. Not even neutron degeneracy pressure, that too is crushed. There is no known force in physics that can halt this final absolute victory of gravity. The core collapses and collapses and collapses. It passes the density of a white dwarf. It passes the density of a neutron star. It keeps going. According to Einstein's theory of general relativity, the core collapses all the way down to a point with zero size and infinite density. This point is called a singularity. This object, the remnant of this impossibly large star, is a black hole. It's crucial to understand what a black hole is. It is not a monster. It is not a cosmic vacuum cleaner that roams the galaxy, sucking things up. A black hole is simply a place where gravity has become so strong that it has fundamentally warped the fabric of reality. Think of spacetime, the 3 dimensions of space and the one of time, as a flat, stretchy rubber sheet. A planet like Earth is a small ball creating a gentle dimple. A star is a bowling ball creating a deeper curve. This curve is what we feel as gravity. A neutron star is like a tiny, super heavy pellet creating an incredibly steep, deep funnel in the sheet. A black hole is an object so heavy and so small that it has punched a hole all the way through the rubber sheet. It creates a pit in spacetime that is for all intents and purposes bottomless. It is a region where gravity has become an absolute, overwhelming and inescapable force. The edge of this pit has a famous name, the event horizon. This is not a physical surface, you could not stand on it. It is a one-way door, a point of no return. The event horizon is the precise distance from the singularity where the escape velocity, the speed you need to go to get away from the gravity, becomes greater than the speed of light. Since nothing in the universe can travel faster than light, anything that crosses the event horizon is trapped forever. If you point a flashlight away from the black hole, the beam of light itself will be pulled back. If you were watching a friend fall into a black hole from a safe distance, you would see strange things. As they got closer to the event horizon, gravity's effect on time would become obvious. You would see their clock appear to slow down. They would seem to move in slow motion, their image getting redder and dimmer. As they reached the horizon, they would appear to freeze completely, fading away over an infinite amount of time, but never quite crossing. But for your friend, their experience would be different. They would feel no bump or barrier at the event horizon. They would sail right through. However, the moment they crossed, their fate would be sealed. Every possible path, every direction they could move in space would now lead them to the singularity at the centre. It would be as inevitable as tomorrow. Black holes are the final extreme statement of gravity's power. They are the point where our understanding of physics breaks down, and where the very fabric of space and time is bent to its absolute limit. They are not monsters, but they are the universe's most profound and final endpoints, born from the death of its most magnificent stars. For over 2 centuries, the world operated on a beautiful, simple, and incredibly accurate idea of gravity. Isaac Newton, watching an apple fall, imagined that the same invisible force plucking the apple from the tree was also the force keeping the moon in orbit around the Earth, and the Earth in orbit around the Sun. He called this gravity an instantaneous universal force of attraction, a pull that every object with mass exerts on every other object. His equations were so precise they could predict the motion of planets, the timing of tides, and the path of a cannonball. And yet, for all its power, Newton's gravity had a deep, dark secret that bothered Albert Einstein. How did it work? How did the Sun 93 million miles away know that the Earth was there? How did it pull the Earth through empty space? Newton himself admitted he did not know the mechanism. He just described the effect. To Einstein, this spooky action at a distance felt like magic, not physics. It also violated his new theory, special relativity, which had established that nothing, not even information, could travel faster than the speed of light. If the sun suddenly vanished, Newton's gravity implied the Earth would instantly fly off into space. Einstein's theory insisted that the news of the sun's disappearance couldn't reach Earth for over 8 minutes. Einstein needed a new theory of gravity. He found his first clue in what he called his happiest thought. He imagined a man falling from the roof of a house. As the man falls, he doesn't feel his own weight. If he were to drop a ball from his hand, the ball would float beside him seemingly weightless. In that moment of freefall, gravity seems to disappear. Now imagine that same man in a rocket ship deep in outer space, far from any planet. There is no gravity. He floats. But if the rocket suddenly fires its engines and accelerates upward, the man will be pressed to the floor. If he drops a ball, the floor will accelerate up to meet it, making it look exactly as if the ball fell. From inside his windowless room, the man has no way to tell the difference between upward acceleration and downward gravity. This was the revelation, the equivalence principle. The effects of gravity and the effects of acceleration are perfectly indistinguishably the same. This might seem like a simple observation, but Einstein realized it had a profound consequence. If the man in the accelerating rocket shined a flashlight beam across the cabin, the beam would appear to bend. It travels in a straight line, but the rocket floor is moving up so fast that by the time the light reaches the far wall, it hits at a lower point. The path of light looks like a curve, and if acceleration and gravity are the same thing, then gravity must also bend light. This was a problem. Light was considered pure energy, it had no mass. According to Newton's formula, which depended on 2 masses pulling on each other, gravity should have no effect on light at all. Einstein realized Newton wasn't just slightly wrong, his entire concept of gravity as a pull had to be replaced. Gravity was not a force, it was something far stranger. After 10 years of intense mathematical struggle, Einstein unveiled his masterpiece in 1915, the general theory of relativity. His answer was not a force, but a fabric. He proposed that the 3 dimensions of space length, width, depth, and the single dimension of time are not separate. They are woven together into a single 4-dimensional entity called spacetime. This spacetime fabric is the stage on which all of reality plays out. When there is no matter or energy, this fabric is flat, rigid, and predictable. Objects moving through it travel in perfectly straight lines, just as Newton imagined. And this is the core of the entire theory matter, and energy changed the shape of that stage. Mass does not pull on other objects. Instead, mass tells spacetime how to curve, and curved spacetime tells matter how to move. Gravity, Einstein declared, is nothing more than the warping, bending, and curving of the fabric of reality itself. It is an invisible geometry. Where Newton saw a force pulling the Earth toward the Sun, Einstein saw the Sun's immense mass creating a deep dent in the spacetime fabric. The Earth is simply rolling along the edge of that dent. The most common way to visualize this is to think of reality as a giant flat flexible rubber sheet or a trampoline. This two-dimensional sheet represents our four-dimensional space-time. If you place a bowling ball representing our sun in the middle of this trampoline, what happens? It sinks, creating a deep curved indentation in the fabric. The trampoline is no longer flat. Now roll a small marble representing the Earth onto the sheet. Don't aim it directly at the bowling ball, but roll it past the side. The marble will try to travel in a straight line, but the fabric it's rolling on is curved. As it gets near the bowling ball's dent, its path is deflected. If you roll it with just the right speed and angle, the marble won't fall into the center, nor will it fly off the edge. It will settle into a stable path circling around and around the central depression. It is in orbit. From a distance, it looks just like the bowling ball is pulling the marble. But if you look closely, there is no invisible string, there is no force. The marble is simply following the straightest possible path, what mathematicians call a geodesic, through a curved surface. This is our solar system. The Earth, the planets, and the comets are not being pulled by the sun. They are traveling in what they think is a straight line, but the space-time they are traveling through is warped by the sun's mass. We experience this warp as gravity. A heavier object like a neutron star would be a much heavier ball on the trampoline, creating a far steeper and deeper curve. A planet would have to orbit incredibly fast to avoid falling in. An object with the ultimate mass concentration, a black hole, is not just a dent in the fabric, it's a puncture. It's a point of infinite curvature, a well so deep that even light moving at the fastest speed possible cannot find a path out once it crosses the edge. This new theory was elegant, but was it true? Einstein proposed 3 tests. The first was to see if gravity could really bend light just as his thought experiment predicted. If the sun truly bends the space-time around it, then the light from a distant star should bend as it passes by the sun on its way to Earth. This means the star's apparent position in the sky should shift. The problem, of course, is that you cannot see stars during the day. The sun's own light blots them out. But there was a solution: a total solar eclipse. In 1919, the British astronomer Sir Arthur Eddington led expeditions to Brazil and an island off the coast of Africa. As the moon passed in front of the sun, plunging the world into darkness for a few precious minutes, they frantically photographed the cluster of stars, the Hyades, that were in the sky right next to the eclipsed sun. They compared these photographs to others taken of the same star field 6 months earlier, when the sun was in a different part of Thesky. The result was world-changing. The positions of the stars had shifted. During the eclipse, the stars closest to the sun's edge appeared to be pushed slightly outward. The sun's gravity had indeed bent their light. Einstein's prediction was confirmed. Gravity was not a force between masses, it was the curvature of reality. Newspapers around the world announced a revolution. Today we don't just see this effect, we use it. When we look at very distant parts of the universe with powerful telescopes, we often see this gravitational lensing in action. The gravity of a massive galaxy or cluster of galaxies in the foreground will bend and magnify the light of an even more distant galaxy or quasar behind it. Sometimes this lensing effect is so strong it splits the light from the single background object into multiple images, creating a pattern known as an Einstein cross, or distorting it into a beautiful glowing Einstein ring. It is a cosmic telescope built from space-time itself, allowing us to see objects that would otherwise be too far away and too faint. Bending space is one thing, bending light is another. But the most bizarre and mind-bending consequence of Einstein's theory is that if space and time are truly woven together, you cannot bend one without bending the other. If gravity is the curvature of space-time, then gravity bends time. This is not a metaphor. It is not philosophy. Time itself, the very rate at which clocks tick and biology ages, is affected by gravity. The rule is this: the stronger the gravity, the slower time flows. Go back to the trampoline analogy. The dent made by the bowling ball is not just a dip in space, it is also a dip in time. Time runs slower for objects deeper in a gravity well than it does for objects high up far from the mass. This effect, called gravitational time dilation, is incredibly small in our everyday lives, but it is real and it is measurable. In the 1970s, physicists put hyper-accurate atomic clocks on airplanes and flew them around the world. When they landed and compared them to identical clocks left on the ground, the clocks that flew were slightly ahead. They had aged faster than the ground clocks. Why? They had spent hours at 30,000 feet where Earth's gravity is ever so slightly weaker. They were higher out of Earth's gravity well, and time for them ticked just a few billionths of a second faster. Today, this is not just a curious experiment, it is an essential piece of daily technology. Your phone's global positioning system GPS would be completely useless if it did not account for Einstein's theories. The GPS system works by communicating with a network of satellites orbiting high above the Earth. Each satellite carries an extremely precise atomic clock, but two relativistic effects are at play. Special relativity. The satellites are moving very fast, about 14,000 kilometers per hour. As special relativity dictates high-speed motion slows time down, this effect makes the satellite clocks run slower than ground clocks by about 7 microseconds, 7 millionths of a second every day. General relativity. The satellites are far above the Earth where gravity is much weaker. As general relativity dictates, weaker gravity makes time run faster. This effect makes the satellite clocks run faster than ground clocks by about 45 microseconds every day. The net result is that the clocks in orbit gain about 38 microseconds, 45 minus 7 every single day. That might sound tiny, but GPS relies on timing signals that are accurate down to the nanosecond billionth of a second. If the engineers did not build in corrections for Einstein's time-bending reality, the system's navigation errors would accumulate. Your phone's GPS would be off by about 10 kilometers every single day. The entire system would fail within minutes. Every time you use a map on your phone, you're proving that time flows at different rates in different places. You're demonstrating in the palm of your hand that gravity is not a pull, but a profound and beautiful distortion of the very fabric of space and time. It all begins in the quiet, immense dark. Before the first light, before the first star, there was only a vast expanding sea of simple gas, mostly hydrogen, and an invisible patient force. This force, gravity, was the architect of everything to come. It began its work silently pulling tiny individual atoms together. At first, nothing seemed to happen, but over millions and millions of years, gravity's gentle, persistent tug gathered these atoms into unimaginably large, cold, dark clouds. These clouds were the nurseries of the cosmos. As these clouds grew, gravity's pull became stronger. The clouds began to collapse under their own immense weight. Gravity was squeezing them tighter and tighter. In the very center of these collapsing clouds, the pressure and temperature began to rise, building to a point of impossible heat. This is gravity's first great miracle. It squeezed the simple hydrogen atoms so tightly that they fused together, becoming a new element, helium. In that moment, a tremendous burst of energy was released. A star was born. Gravity, the force that pulls things in, had created the very thing that pushes out light. The universe was no longer dark. Across the vastness of space, gravity was switching on the lights one by one. These first stars were giants, and they lived fast, spectacular lives. They burned through their fuel, but they held a problem. They could only create the simplest elements. The universe was still missing the key ingredients for life as we know it. It did not yet have the complex materials needed to build planets or people. This is where gravity stepped in to perform its second most violent and most creative act. When one of these giant stars used up all its fuel, the outward push of its light and heat suddenly stopped. With nothing holding it back, gravity won the final battle. The star's massive core collapsed in on itself in less than a second. This catastrophic collapse triggered the most powerful explosion known to the universe, a supernova. This explosion was not just an end, it was a creation. The energy of this gravitational collapse was so immense that it acted as a cosmic forge, smashing simple atoms together to create all the heavier elements. In that fiery instant, the universe was seeded with carbon, the fundamental building block of all life. It was filled with oxygen, the element that would one day fill our lungs and form the water in our oceans. And it was gifted with iron, the heavy metal that would one day form the core of our planet and the very blood that runs through our veins. This stardust, this rich collection of new heavy elements, was blasted out into space. The first stars had to die so that we could live. Gravity was not finished. Once again, it began its patient work. It gathered these new enriched clouds of dust and gas. It pulled them together. But this time the ingredients were different. As this new cloud collapsed, it formed a new star in the center, our sun. And in the spinning disk of dust that surrounded it, the leftover bits of carbon, oxygen, and iron began to stick together. Gravity pulled these clumps into larger and larger bodies. These became the planets, including our own small blue world. This is our home, but we are not just living on the Earth, we are the Earth. The planet we stand on is made of that same iron and oxygen from a star's death. The life that emerged from its oceans is built from that very same carbon. We are in the most literal sense made of stardust. We are the direct products of gravity. Think about what this means. Gravity is not just something that keeps our feet on the ground. Gravity is our ancestor. It is the force that first gathered the gas. It is the force that ignited the stars. It is the force that forged the atoms in our bodies. It is the force that collected those atoms to build our world. It is the force that holds our atmosphere in place, allowing us to breathe the very oxygen that a long-dead star created. This is our true place in the universe. We are not separate from it. We are a continuation of it. We are the part of the cosmos that after 13 billion years has finally woken up. The carbon atoms in our brains, forged in a supernova long ago, have now organised themselves in such a complex way that they can look back out at the sky. We can see the other stars and understand the story. We are the universe becoming aware of itself. We are the cosmos contemplating its own beauty. So as you rest, feel the gentle weight of your body. That feeling is your personal connection to the cosmos. It is gravity tying you to the Earth. But that same force, that same fundamental rule is what is holding the moon in its orbit right now. It is the same force that is holding the entire Earth in its path around the Sun. It is the very same force that is binding the hundreds of billions of stars in our Milky Way galaxy, keeping them from flying apart. The connection you feel is real. The atoms in your body are obeying the same law that orchestrates the grand dance of the galaxies. You are not small or insignificant. You are a piece of the whole as essential as any star. You are a child of gravity woven into the fabric of space and time. Let your mind drift on that thought. Feel that quiet, unbreakable connection to everything. You are not just in the universe. You are the universe. And in this moment you are safe. You're home. Allow that profound sense of belonging to carry you into sleep.